This is a satellite dish that has never moved, not once. No motor, no gimbal, no moving parts of any kind. And yet, right now, it is tracking a satellite racing across the sky at 27,000 kilometers per hour. How? The first time engineers saw this done, most of them didn't believe it. It looks like the antenna is reading your mind, aiming itself instantly in any direction you want, with nothing inside it capable of turning. It seems to break a basic rule of physics, that to point somewhere new, something has to move. But it doesn't. And the trick behind it isn't hidden in some classified vault. It's sitting in almost every modern piece of technology you rely on. Starlink terminals on rooftops, 5G towers on street corners, missile defense radar, deep space communication dishes. All of them use some version of the same idea. And once you see how it actually works, you'll never look at a satellite dish the same way again. To understand it, we have to go back to a problem engineers ran into during the Second World War. Early radar systems had a serious limitation. To scan the sky for incoming aircraft, the entire dish had to physically rotate. That's slow, and slow is dangerous when you're trying to detect a bomber before it's overhead. Engineers needed a way to sweep a radar beam across the sky without waiting for heavy machinery to swing around. And the answer came from a strange place. Not from moving the antenna, but from timing. Let's start simple. Imagine a single antenna broadcasting a radio wave. That wave spreads out in every direction, like ripples from a stone dropped in a pond. Useful, but wasteful. Most of that energy goes nowhere near your target. Now add a second antenna a short distance away, broadcasting the exact same signal at the exact same time, where the waves from both antennas arrive in step, peak lining up with peak. They reinforce each other. Where they arrive out of step, peak meeting trough, they cancel out. In some directions, the signal gets stronger. In others, it disappears almost entirely. This is interference, and it's not a bug, it's the whole trick. Here's the part that matters. What if, instead of firing both antennas at exactly the same time, you delayed the second one by a tiny fraction of a second, just a few trillionths of a second, some fraction of the wave's own cycle? That small delay shifts where the waves line up and where they cancel. And that shift changes the direction the combined signal points. You haven't moved either antenna. You've only changed the timing of the signal reaching them. And that alone was enough to redirect the beam. This is the entire secret of a phased array antenna. Not movement, timing. Let's build the intuition further, because at first, this feels almost too simple to be responsible for something as sophisticated as tracking a satellite across the sky. Picture a line of people standing at the edge of a swimming pool, each holding a paddle, and each one dips their paddle into the water at the same moment. You get a straight wave traveling directly outward, perpendicular to the line of people. That's your basic case. All antennas firing in sync, beam pointing straight ahead. Now, instead, have the person on the left dip their paddle first, then the next person a moment later, then the next, each one just slightly delayed from the last. What happens to the wave now? It doesn't travel straight out anymore. It tilts. The wavefront angles itself in the direction of the delay. Like a marching band turning a corner by having one side take slightly longer steps. That tilt is your beam steering. The physical antennas never moved. The people never moved. All that changed was the timing between them, a cascading delay running down the line. And that timing alone was enough to redirect where the energy travels. Real phased array antennas do exactly this, except instead of a handful of people with paddles, you might have hundreds or even thousands of individual antenna elements, each one a tiny transmitter and receiver arranged in a flat grid. Each element gets its own tiny, individually controlled timing delay, called a phase shift. By carefully calculating the phase shift for every single element, engineers can point the combined beam anywhere they want, and they can do it in microseconds, far faster than any motor could physically turn a dish. Want to track a satellite moving overhead? You don't rotate anything. You just recalculate the phase delays thousands of times per second, and the beam sweeps across the sky as if it were being aimed by a machine with no moving parts at all, because it is. This is where the real engineering challenge begins though, because getting this right requires almost impossible precision. Remember, the entire trick depends on tiny timing differences between elements, fractions of the wave's own cycle, at the frequencies used by radar and satellite communication. These delays can be measured in picoseconds, trillionths of a second. If even one element in the array is off by a small fraction of that timing, the beam doesn't point where you want it to. Worse, the reinforcement pattern can partially break down, and this energy that should have combined into a tight, powerful beam instead leaks out in unwanted directions, called side lobes. Too much error, and instead of a sharp focus signal punching through to a distant satellite, you get a weak, smeared mess pointed vaguely in the right area. So every single element in the array needs its own precisely controlled phase shifter, tiny electronic components capable of introducing an exact, adjustable delay to the signal passing through them. And in a large array, that might mean thousands of these components, all synchronized, all recalculated continuously as the target moves. This is also why phased arrays were, for decades, reserved almost exclusively for military and aerospace applications. The individual components, the phase shifters, the signal processing hardware, the calibration systems were extraordinarily expensive. Early phased array radar systems cost hundreds of millions of dollars, restricted to fighter jets, missile defense installations, and spacecraft where the ability to track a target instantly with no moving parts to fail was worth almost any price. But there's a deeper reason phased arrays matter beyond just speed. A mechanically steered dish can only track one target at a time. It's pointed in exactly one direction, full stop. A phased array, because it steers electronically rather than physically, can do something a moving dish simply cannot. It can split its attention by adjusting the phase pattern across different subsets of elements. The same physical array can track multiple targets simultaneously or send data to several satellites at once, all without moving a single component. This is part of why modern satellite internet systems and advanced radar installations rely on this design. It isn't just faster, it's fundamentally more capable. Let's bring this back to something you may have seen recently: those flat, pizza box-sized panels used for satellite internet terminals. From the outside, they look almost unremarkable. A flat white or black panel, no dish shape, no visible moving parts, sitting quietly on a rooftop. But underneath that flat surface is a densely packed grid of individual antenna elements, each with its own phase shifter, all coordinated by onboard processors recalculating timing delays continuously. As the satellite it's communicating with moves across the sky, the terminal doesn't physically move to follow it. It recalculates its phase pattern, tilting its invisible beam electronically, tracking the satellite until it drops below the horizon, then instantly reacquiring the next satellite rising to take its place. All of this happens continuously, silently, with zero mechanical motion. For decades, this kind of capability existed only in military radar systems and NASA's deep space communication arrays, because that was the only place the enormous cost of thousands of precision phase shifters could be justified. What's changed is that the electronics needed to make each of these tiny phase shifters have become dramatically cheaper and easier to manufacture at scale, the same trend that's made microchips cheaper for everything else. That's what has pushed phased array technology out of exclusively defense and space applications and into rooftop internet terminals and 5G cell towers. There is, however, a genuine limitation worth understanding, because it explains why phased arrays haven't fully replaced traditional dishes everywhere. As you try to steer the beam further and further away from pointing straight out from the array's surface, the effective size of the array, as seen from the direction you're pointing, shrinks. Tilt the beam too far toward the horizon, and the array essentially appears edge-on to the target, dramatically weakening how much energy actually reaches it. This is why phased array terminals typically have a usable field of view rather than being able to track a satellite completely from horizon to horizon beyond a certain angle. The physics of the array geometry works against you no matter how precisely you control the timing. Engineers work around this in different ways. Some designs use multiple phased array panels, each covering a different angular range, so as a satellite moves out of one panel's effective field of view, another panel picks up tracking duties. It's a bit like a security team handing off surveillance of a moving target from one camera to the next as it crosses zones, except here, the handoff happens automatically and near instantly. So the antenna that never moves isn't magic, and it isn't secret, even if it still looks like witchcraft the first time you see it work. It's the result of an idea that seems almost too simple. Control not where your antennas are, but when each one fires. Get that timing right, down to trillionths of a second, across potentially thousands of elements simultaneously, and you can steer a beam of energy anywhere you want, faster and more flexibly than any motor ever could. It's the same underlying principle at its core as those two antennas we started with. Two overlapping ripples in a pond, reinforcing here, canceling there. Scale that idea up, refine the timing to an almost absurd degree of precision, and you get a technology quietly running underneath GPS navigation, 5G networks, satellite internet, and some of the most advanced radar and space communication systems ever built. No moving parts, just perfectly, deliberately, out-of-step timing turned into precise control over where energy in the universe decides to go.